We talked about what happens as you go across the periodic table. Okay. So if we, there we go. We have our, you can barely see it, hydrogen, 1s1. All right. But let's start with something interesting like potassium. There's potassium. Here's the electrons, 1s2, blah, 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 blah. Here's the electron configuration. All works out according to a rule. And then we marked the outer orbital, which is the s orbital. And we go across the periodic table. We're adding more electrons. And boom, 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 boom. We're adding into d orbitals. Now the p's, which are in red. And then what happens to the size as you move this way? It was there. Now the new part, if you can see it, kind of part, is right there. Oh, it's not 100%. Like there are, it does. It shrinks a little bit, but not a lot. All right. And then it starts to contract a little more. So it is from the left to the right. The overall trend is it gets smaller. There are exceptions in there. Okay. All right. So it's not 100% true, but in general, we're looking at trends here. You go across the periodic table, the size of the atom shrinks. Why? Why does the size of the atom shrink?
Because there's more protons, which attack the
Yeah.
electrons.
You're putting more protons into the nucleus, which pulls the electrons in. Okay? So, what does this mean? Ionization energy is the energy required to create an ion, i.e., to remove an electron. Okay? To remove an electron. How much energy does it take to pull an electron off this atom? I'm going to call it IE because I'm... All right. So, if you are a bigger atom, so here's your nucleus. I don't have my cookies anymore. We have my tea. This is the nucleus, and you're way out here as compared to an electron that is right here. Which one is easier to pull off? The further one, right? I.e., the larger the atom. So, the force of attraction between the nucleus and the atoms increases. Excuse me. As the force of attraction between the nucleus and the atoms increases, more energy is needed to remove the electrons. So, the ionization energy decreases going down a family. All right? Because if you look here, if we go back to this, we go to sodium, right? We go from sodium to potassium to rubidium. Actually, I should mark these. Sodium. There's Li. And then if you go to sodium, Na, you're adding s orbitals, right? Potassium. So what's happening is the atom's getting bigger. The outer electrons are getting further away from the nucleus, so the nucleus has less pull on them, so it's easier to pull the electron off. Okay, so the ionization, the amount of energy required to do that, decreases. Okay,
So that's why the metals get more reactive with water.
and that's what we're going to show on Monday.
Oh,
All right.
cesium and water.
So yeah, you can't get cesium. So the ionization energy decreases going down a family. More energy levels means more the valence electrons are further away. Now, going across, we said, what happens to the size of the atom as you move across the table? It shrinks, right? So that means the electrons are closer to the origin or to the nucleus, which means they're held more tightly, which means the ionization energy, the energy required to pull the electron off, goes up. Okay? So ionization energy increases left to right. More protons in the nucleus means more attraction between the nucleus and the elements.
So when the lowest energy for an element is francium, so it's like
Yeah.
the lowest.
So francium, Fr, has the lowest ionization energy. It's the easiest to rip that electron off. Okay? And if you look on the periodic table, this is not a complete periodic table. So here's francium down here. It's the lowest. Okay? Because it increases going this way. So that means the lower energy levels are going to be over here, ionization energy. And ionization energy decreases going down. So francium is lowest. Where's the highest?
Helium.
Well, helium's a noble gas. It's fluorine. Okay, it's got one valence. It's got whatever valence electrons. It does not want to lose its electron. Okay. So francium has the lowest ionization energy. And we'll say F. Highest. We're not counting noble gases. Okay. Okay, we already talked about the atomic radius. All right. As you go down a periodic table, the size or the atomic radii of the atoms gets bigger or smaller? It gets bigger, right? Which is a result of more shells. As you go across the periodic table, left to right, what happens to the size? It gets smaller. Because you have more electrons and more protons pulling them in. Okay. A lot of chemistry comes down to is a result of these simple ideas. How far away are the electrons from the nucleus, which means how reactive or how easy is it to pull off? Because all a reaction is you're basically sort of transmitting electrons, not transmitting, transferring electrons or sharing electrons. Okay? So this leads to the idea of electronegativity. All right? Electronegativity is how badly an atom wants an electron. Okay? And it doesn't want it because it's not thinking, but how badly it can pull electrons. Okay? So the tendency for atoms to attract electrons from neighboring atoms.
So like the higher the electronegativity, like the more they want electrons.
Yeah. So the higher electronegativity means the more they want to pull electrons. Okay? So atoms with high electronegativity attract electrons from neighboring atoms. It doesn't have to be different, like it can be within a molecule, and I can show you. Actually, I can show you today, actually. To attract other electrons from neighboring atoms. Fluorine is the most electronegative, all right? Which coincides with its size, right? Fluorine is a small atom, right? Because we went across the periodic table, size decreases. And we know if size increases going down, it decreases going up. So fluorine has the highest electronegativity. It also has the highest what? We just said it. Ionization energy. High electronegativity means high ionization energy. It doesn't want to give up the electron. It wants to grab an electron. Low ionization energy means
that you want to lose.
low electronegativity, so it doesn't hold on to its electrons very strongly. This is why in grade 10 or all the other grades, and even this grade up to a certain point, we always just said, we talked about electronegativity, we just never gave it a name. We said fluorine wants to gain an electron, right? Why did it want to gain an electron? So then it could be like noble gas, it'd be isoelectronic. Now we know what that electron configuration looks like. And it's because this is highly electronegative and it's small. The alkali metals don't want to gain an electron because the electrons are far away from the nucleus because these are all s orbitals. So they lose the electron, usually to a more electronegative atom that pulls it, and you get an ionic compound forming. Okay? So you've already talked about this. Now we're sort of just giving it names. Okay? All right. Okay, so here's a summary of the trends. So electron affinity, the ability to want an electron, increases left to right. This is essentially, let's call this electronegativity. Which coincides with increasing ionization energy, the energy required to pull the electron. If it's holding on to it tight, it's going to take a lot of energy to rip it off the atom. Ionization energy increases going up, as does electron affinity, but let's call it electronegativity again. Why are we not working? Which coincides with decreasing size. The atomic radius increases this way and going down. So big, low ionization energy, low electronegativity is down here. Small atoms with high electronegativity and high ionization energy are over here. Okay? You need to be aware of these trends on the periodic table. Okay? Because I could ask you, here, I could say, which is more electronegative, bromine or fluorine? Fluorine's too easy. Let's say oxygen or selenium. It's going to be oxygen because it's above, right? Electronegativity increases going up. These are smaller atoms, so they hold on tighter. Which is larger? Barium or gold? Barium. Here's barium. Here's gold. Increasing atomic radius. Going this way. Okay? The questions like that are fair game. All right? All right. No, I'm not going to give you the exceptions because that's just memorizing the exceptions, and I just want you to understand trends. All right, this is not a quantum chemistry class or a quantum physics class. Okay, before I get you to do these questions in the book, I'm just going to show you this, and I can show you a demo. So, what molecule is this? That's water, right? And this is leading into the next unit that we're going to talk about. Which is more electronegative, oxygen or hydrogen? It's oxygen. If you look at your periodic table, here's oxygen, here's hydrogen. Okay? Oxygen oxygen wants electrons. Okay? So what actually happens in water, and I can demonstrate this, is, and we're going to learn what this notation is, the oxygen pulls the electrons towards it. All right? So you get more electrons around the oxygen than you do the hydrogen. So it creates a charge on water. Nobody ever thinks of water as having a charge. So you don't need to worry about the symbol. This means a partial negative charge is on oxygen. And because you pulled electron density away from the hydrogens, you get a partial positive charge. This idea, it's not an idea, this thing, this phenomenon is the reason we have life on Earth. Because what this does is when it interacts with other water molecules, this is partially negative, this is partially positive. Positive and negative attract to each other, right? So you get these things attracting to the negative. This is why water is a liquid at room temperature. Okay, it's theoretically, if this didn't happen, it would be a gas at room temperature. And if we have gas, if water is not liquid, you can't have life. Okay? It's also the reason that ice floats, right? So what happens, that's like one of the only things that floats in solid form is less dense than the liquid form. All right? So water, when it's liquid, they're smashing into each other because they have energy, and we're going to talk about this in the next chapter. They can get really close. But when you start to cool them down, they form a crystal, which is ice. All right? And they freeze, and they're actually farther apart. So they become less dense, and that's why ice floats on water. Well, that has to do. So that has, you have your. It's the same idea. Here, the glass has a charge too, right? It's got electrons. It's made of atoms, and the water has a charge. So you're getting, I can't remember if it's the negative or the positive. One of them is attracted to the glass, right? So it's bonding to the glass, like hydrostatically bonding. The atmosphere is pushing down on this, right? So you get this little curve. It starts to sort of climb up a little bit. But this stuff has nothing to bond to. So these molecules are sort of stuck to the side, and you get a bit of pressure pushing down. All right? If you actually boil water at, I'll try to show you this next week. You can boil water at lower temperatures, right? If you go up to a mountain or something, really high mountain, there's less air pressure on the water, so it'll boil at slightly under 100 degrees. Because what's happening is you're heating up the water, you're breaking these bonds, these interactions, and you have to go to 100 degrees to overcome the atmospheric pressure. But if there's less atmosphere, because you're higher, it's less pressure, so it takes less energy to boil the water. But I can show you a sort of demo of that in class if we have ice. Sorry, what? Like these things? Because oxygen is more electronegative, so it pulls the electrons closer to it.
So what about
like a big molecule?
Yeah.
You get a lot of different distractions, and then not distractions, separations, and that can determine how things fold in space. So anybody taking biology, have you looked at protein structure and stuff? Do you do that in grade 11 bi? Yeah? Are you in grade 12 bi? So you talk about like primary structure, secondary structure, tertiary, and then quaternary, the fourth degree structure is how it folds. That has to do with this kind of stuff too. Same with DNA, electronegativity, the bonding of the bases and stuff. Like if okay, hang on. Now we're just going.